Hi, welcome to section 5. In today's section, what I'm going to cover is I'm going to cover gains and losses from trade in the specific factors model. So this is part 2 of the videos that I'm going to post for the week of September 28th. The other video goes back to section 0 and covers percentage changes. And so that's going to be useful for some of the material that I'm going to cover in today's section. So if you haven't watched that video yet, I encourage you to go back to section 0 and cover percentage changes, or to watch that video before getting started. So what did we do in last week's section? Last week's section, we introduced the specific factors model. And in this section, we're going to basically start right off where we left off the last time and use the exact same setup for the specific factors model as in section 4, where you have a question where there's the US and Japan, and they're both going to open up to trade. So because we're going to start off right where we left off in section 4, if you're unfamiliar with the setup of that problem, I'm not going to go over it again. And so it's going to be useful to look back over that video again or review the section notes. And so please review section 4, problems 8 before watching this video, because I'm going to start off directly from problem 9, assuming that that's familiar in your memory. So you might want to pause here, go back, review it, and then pick back up. And so we're going to continue on from problem 8, where we left off last time. And what I'm going to show you today is I'm going to show you in this model, there's going to be 3 different types of groups. There's going to be laborers who sell their labor at wage W, and then there's also going to be, and this is now new in the specific factors model, there's going to be owners of land and capital. And for each of those 3 groups, we're going to determine who gains, and what's new is now potentially loses from trade. And so if you go back to the Ricardian model, recall that there's only one factor of labor, or sorry, only one factor of production, labor. And in the Ricardian model, we always see that labor gains from trade when 2 countries move to autarky to trading with each other. And so it's going to be helpful to compare this to the Ricardian model, where everyone always gains from trade. And so now the specific factors model can tell us a little bit about the potential distributional consequences of trade, such as, now it might not be that everyone is going to gain from trade. It might be that trade is going to create winners and losers. And so I'll come back to that point when I get there. And so, as I said, I'm going to jump straight in with where we left off in section 4, problem 8. And I'm going to start off with a new question. So this is problem 9 on section 5. And so what I'm going to do is I'm going to assume that LM is equal to LA under autarky. And what I want to figure out is how much LM and LA are going to change in Japan upon opening the trade. So what I'm going to assume is I'm going to assume that by however much LM and LA are eventually going to change, then LM prime and LA prime are going to be the new values of how many workers are in manufacturing and agriculture when Japan opens up to trade. And so it's helpful to review some of the assumptions that we need. And let me check. And it's going to be helpful to review some of the assumptions that we need. So first, let's note that we want to have that we have full employment of both factors in our country, both before and after we open up to trade. So what does that imply? That implies that if we add up workers in manufacturing and agriculture in Japan, they must equal the full population in Japan. The same must be true for the new values of labor employed in manufacturing and agriculture. And so then, for instance, going back to percentage changes and what you saw in section 0, you can note that if we know what LM is and we know what LA is, then, if we know what LM prime is. So if we know what LM prime is, and we know what LM is, then we can relate these two by saying that that LM is related to LM prime by just increasing it by X%, or by multiplying it by 1 plus X% divided by 100. Okay. Likewise, we're going to have that LA prime is going to be equal to LA if we can assume that LA might decrease because that's going to be the factor in which we don't have a comparative advantage in. And so we're going to say that LA is related to LA prime by just reducing by Y%. And so that's one way to write this. And so this is saying, this is all we're saying is that LM is going to increase X% to whatever LM prime is, and LA is going to decrease Y% to LA prime. Okay. So, so now what does that give us? Okay, well, we can do a couple things. We can note that if we substitute in for LM prime and LA prime here in this expression, our full employment expression, we know that we can just rewrite this expression here as this. Now I'm just taking their new values and rewriting them with their initial values, knowing that each is going to increase or decrease by X and Y respectively. And now the fact I'm going to use is I'm going to use that I know that, actually, you know what, let me multiply these terms out here. So if I multiply these terms out, what do I get? I get LM plus LM X % over 100 plus LA plus LA Y% over 100 equals L bar. And so then all I'm going to use is I'm going to use the fact that LM is equal to LA to substitute for wherever LA shows up here. And so what I'm going to do I'm just going to substitute in LA for LM on both sides of this. Okay, what does that give me? That gives me 2LM plus, and here I'm just going to pull the LM out of both these terms. What will that give me? That'll give me X plus Y%, so X% plus Y% over 100 needs to be equal to L bar. Okay, but if I have that LM plus LA initially equal to L bar, then what does that tell me? That tells me that knowing that LM is equal to LA, then I have that 2LM is equal to L bar. And so this taken all together, this is going to imply that LM times X% plus Y% over 100 must be equal to 0. You can see that because I subtract 2LM or L bar on both sides. Okay. But suppose that we didn't have that the amount employed of labor employed in manufacturing was 0, and the reason you can generally assume that is because with Cobb-Douglas preferences in autarky we would generally consume some combination of both manufacturing and agriculture. So I can assume that the amount of labor in agriculture was not 0, And so that means if this term is 0, this and LM is not equal to 0, then this implies that one of the sum of x% plus y% has to be equal to 0. Okay, so in other terms, the amount of labor that we lose from sector A has to equal exactly the percentage of labor that we gain in sector M. So I'll come back to this rule. This will be useful later on. Okay. And so the slides tell me exactly what I have on the board. That the amount that x is changing has to be equal to the amount that y is changing. Okay, so now we know that, and this is from last time, we know that the amount that LM over LA is changing so we know that the amount that LM over LA is going to change, and this is coming from section 4, problem 8. We know that LM over A increases by 30% when Japan opens up to trade. And so what is that going to tell us? Well, using the percentage change rules from section 0, we know that the percentage that LM over LA is going to change. And so if you're confused by this notation here, note that the percentage change is a short, the percentage change of LM over LA, which is what I'm calling this, is the same thing. I could write the same thing as delta LM over LA over LM over LA times 100%. And so in the section notes, you'll see that this is written down. In the slides, I like to use this notation because I think it's a little bit easier. But I want to be clear that if you look at the section notes and you look at the slides and they look different, it's not because we're doing anything different. It's just because I'm calling the percentage change in this variable here. I'm just defining it to be this term. And so I'm doing the same thing. I just think that this is easier to write. Okay. Okay, so going back and thinking about the percentage change rules that we learned in section 0, note that the percentage change of LM over LA is equivalent to saying that it's going to be given by, or at least this is going to be approximated by, the percentage change in LM minus the percentage change in LA. How can you see that? You can see that because LA, by being the denominator, technically has a exponent of -1, and so that comes out like so. Okay, so the percentage change in LM minus LA must equal to 30%. But recall that we said last time in the last slide that the percentage that LM is going to change by, well, we just called that x%, and the percentage that LA is going to change by, recall that we just called that -y%. Okay, and so adding all this up, well, that's going to imply that x% plus y% must be equal to 30%. But recall that I said last time that that we have that x% is equal to y%. And so if x plus y% is equal to 30 and x is equal to y, then of course that must mean that both x and y%, so both of them must be equal to 15%. And so we know here that LM is going to, the change in LM, well, that's going to be 15%. And then all we need to do is, it's the same for LA, but the opposite sign. And so LA is going to decrease by 15%. So notice that if LA is in the denominator and it's decreasing, then it increases LM over LA. Okay, and so both these changes add up to the 30% change in LM over LA that we saw last time. So how much do LM and LA change in Japan upon opening trade? Just going to the slides. We have that LM increases by 15% and LA decreases by 15%. So moving on to the next question. We assumed in section 4, problem 8, that the price ratio, PM over PA, increases by 10% upon Japan's opening to trade. And so now we're going to make this a little bit more constant. So before, all we knew was that PM over PA just increases by 10%. So now we're going to assume that PA stays constant, or the percentage change in PA is just equal to 0%. And so then, just using the rule that we have that the percentage change in PM over PA is approximated by the percentage change in PM minus the percentage change in PA. Well, if PA is equal to 0 and this expression is equal to 10%, then that implies that the percentage change in PM is just equal to 10%. Okay, so all of this to say is, now that we've made this assumption, we now know what precisely each price is going to change by, and so this is a little bit stronger than knowing solely what their relative what the relative price is going to change by. And so then problem 10, giving us this information, then asks us in part A to calculate the percentage change in the wages of Japanese workers upon opening the trade. And so there's two ways we can do this. Note that in the specific factors model, unlike in the Ricardian model, it's going to be fairly rare that in the specific factors model we're fully specialized in one good. The reason that you can sort of see that is that in the specific factors model, our PPF is curved, and so for any given price ratio, it's going to be likely that the point at which the slope of the PPF is equal to the relative price is much more likely to be an interior point, and it's going to take a really sort of high price ratio. So one good is going to really need to be relatively much more expensive than the other in order for us to be fully specialized, which is here at a point like here. So it's going to be much harder for us to be fully specialized in the specific factors model compared to the Ricardian model. So this is the specific factors model, or SFM, and this is the Ricardian model. Well then, if I draw my PBF in the Ricardian model and I examine any given relative price, well, you're going to see that as long as the relative price is not equal to the autarky price, or the slope of the PPF, or if the ratio of relative prices is not equal to the slope of the PPF, then we're going to see full specialization. And the only way that we're not going to be fully specialized is if the relative price is exactly equal to the slope of the PPF, or the slope of the inverse ratio of productivities. That's going to be significantly harder to do, and so in the Ricardian model, we're going to tend to see full specialization. is common. As opposed to, you can sort of see that we're really going to need to take very steep or very shallow relative price ratios in order for each of these countries to be fully specialized in the specific factors model. Okay, so that was a long way to say that, that in order to calculate the percentage change in Japanese workers upon opening trade, we need to look at the wages of Japanese workers in both sectors of manufacturing and agriculture. So the way that we're going to start is we're going to start by considering the agricultural sector. And so when we consider the agricultural sector, note that from before, you figured out the marginal product of labor in agriculture in Japan. And we found that the marginal product of labor in agriculture is equal to 2/3 times AA times T. So that's the amount of land that that Japan has, or T can stand for terrain if you want to have that be a little bit easier, divided by the amount of labor in agriculture in Japan, and T over LA is all raised to 1/3. So if we know that this is equal to our marginal product of labor, then we can use the rule that we can use the rules of percentage changes to figure out how much the marginal product of labor in agriculture is going to change if LA changes. So it's worth noting that 2/3 AA and T, they're all going to be constant. And the reason is that when we open up to trade, AA doesn't change. Obviously, the 2/3 doesn't change as well. And T, Japan has a fixed amount of land. And so the only thing that's going to change when Japan opens up to trade is the amount of labor in agriculture. And so the amount that MPLA is going to change by, it's only, remember that go back to section 0, watch that video, recall that the only thing that matters for percentage changes are the terms that aren't constant. The terms that are constant we can just ignore, and then the only thing that matters is that LA is raised to the exponent effectively -1/3 here because it's in the denominator, and so this -1/3 is going to come out in front, and then it's just going to multiply whatever percentage change LA is going to change by. Now, why does that matter for calculating the wages of workers in Japan? Well, we know that if we have production in a given sector, then workers are going to get paid their marginal revenue product. And so what's their marginal revenue product going to be? It's going to be given by the price of the good that they produce. In this case, we're considering agriculture, so it's going to be the price of agriculture times their marginal productivity of labor in agriculture. And so if we want to figure out what the percentage change is going to be in wages of workers in agriculture in Japan, well then the percentage change rules tell us that the percentage change in the wages of workers in agriculture is going to be approximately equal to the percentage change in prices of agriculture plus the percentage change in the marginal product of labor in agriculture. So now hopefully you can see why we went back to the marginal product of labor for agriculture, because we're going to need to figure out how much MPLA is going to change by in order to figure out how much wages change by. Well, recall that I said that PA stays constant, and so we know that this term here is just equal to 0. Okay, I'm going to plug in for what I figured out was my expression for percent changes of MPLA. And so PA is, the change in PA is equal to 0, and then the percentage change in MPLA is just equal to -1/3 times the percentage change in LA. Okay, but we know that, and this is coming from problem 9, that LA is going to decrease by 15% when we open up to agriculture. We're going to have a reallocation of workers from agriculture to manufacturing. And so the percentage change in LA is going to be negative 15%. Okay, and so notice that if LA is decreasing, then we need to put a negative here in front of this percentage change. Okay, and so the negative 1/3 times negative 15% is going to be 5%. So in total, what can we conclude? Well, the changes in the wages of workers in Japan in agriculture, they're going to increase by 5% when we open up to trade. Okay, so this definitely could be sufficient to solve for what the percentage wage change of workers is going to be in Japan. Because note that if workers in manufacturing were paid anything more, all the workers would want to go work in manufacturing instead of agriculture. So I claim that that's all the work that we need to do to figure out what the percentage change in wages of agricultural workers is. However, just to confirm that if we go through the math for manufacturing, it comes out to the same answer, let's also try to figure out the percentage change in wages of Japanese workers upon opening up to trade in manufacturing. Okay, so it's going to be a very similar. So I'm going to do a very similar type of thing here for manufacturing.